Hello and welcome to the second lecture covering lecture 24 where we're discussing quantum physics. In this lecture video we're going to talk about the photoelectric effect. Alright, so let's look at the relevant formulas first. Alright, so the first I want to point out that I included this formula here, which is not specific to the photoelectric effect but is in fact the energy of a photon. Zoom in on that a bit. So E is the energy of an individual particle of light. So it's the energy of a photon. Okay. H is Planck's constant. All right, and let me get you the value for that. So that's 6.626 times 10 to the negative 34 joule seconds. Joule seconds because it is actually a constant that has units of angular momentum, which will actually become quite relevant and interesting in the very next chapter when we talk about the Bohr model of the hydrogen atom. F is the frequency of the light. C is the speed of light. Okay, that's another constant of the universe. That one's 3 times 10 to the 8 meters per second, which you'll probably remember from relativity. And then, of course, lambda is the wavelength of the light. Of the light particle, right? Because it's both a particle and a wave. So the reason I say that I'm including this, even though it's not say exactly part of the photoelectric effect and the exact content of the photoelectric effect, it's just so important. We're talking about photons, we're talking about the energy carried by individual photons and how that energy can interact with solids, a metal in this case. So we just can't ignore it. The last time you saw this formula, because I didn't include it in a previous set of notes, would be lecture 14, okay? So essentially, just the idea of a photon is so important that we can't really box it in a single chapter. It covers a lot. Okay, but now let's get to the photoelectric effect proper. All right, so this first line is a bit of a derivation. So collectively, these two lines together are going to be the photoelectric effect. Okay, so let's label that. Okay, so these two lines represent the photoelectric circuit, or relating the photoelectric circuit to incident light. That's what these formulas do. So relating the photoelectric circuit to incident light. Okay? If you want a circuit diagram of the photoelectric circuit with the idea of the stopping potential and how the current is created, then please refer to the previous lecture and the slides there. Okay, there's some great diagrams, great pictures there. Okay, so let's get into the first line, which I mentioned is a bit of a derivation, a justification of what we're doing. So W with the subscript TOT, obviously standing for total, is the total work done on the liberated electrons. That would be the external work being done on them. So total work done on liberated electrons. Okay, so these are the electrons that are getting kicked out of the metal because there's light coming in. The light is causing the metal to absorb energy, and then that metal gets so energetic that some of its electrons just bounce away. Okay? And remember, right, that's the whole interesting thing about the photoelectric effect is that idea could work with waves, right? You're just heating up the metal and the electrons start boiling away. But it turns out that due to the way that this works, due to the way that it's dependent on the wavelength and the frequency of the light, and not just on the intensity of the light. In fact, which electrons are freed is completely independent of the intensity of light. It tells us that the electrons are behaving like particles. They're actually bouncing into the electrons, not just crashing over it like a wave. Okay, but again, I've said this before, refer to the previous lecture. Okay, so that total work would be equal to the charge of one electron times the stopping voltage. Okay, so E is just the fundamental charge. It's the same we've always used lowercase e to represent the charge of an electron. Okay, that's 1.6 times 10 to the negative 1.602 times 10 to the negative 19 coulombs. Okay, so 1.602 times 10 to the negative 19 coulombs. Okay, it's a charge of one electron, the so-called fundamental charge. And then V naught is the stopping voltage. Because the idea is that the stopping voltage is defined as enough voltage to prevent the freed electrons from actually creating a current in the circuit. Okay, you're applying so much back voltage that even though these liberated electrons are coming out, they're not actually able to then flow through the wire. Okay, because remember there's that vacuum gap, and the idea is that you're stopping the electrons from actually completely jumping that vacuum gap. Okay, that would be equal to the change in kinetic energy of the electrons, right? Because even if they're getting stopped by the stopping voltage, they still jumped out of the metal, flew across some or most of the vacuum gap, and just didn't quite make it to the other side of that vacuum gap, and thus flow through the wire, okay? So there's still a significant change in I almost said potential energy, a significant change in the kinetic energy of the electrons, okay? And so delta K, Z minus K max, because K initial is zero. Okay, so K initial is 0. So then we have that the change in kinetic energy is just negative 1/2 mv squared max. Okay? So this is the change in kinetic energy of the electrons. Okay? And actually it's K final is 0, because at the end they're going to be at rest, right? So they have some initial kinetic energy from the minute they're crashed into by the photon. That's when they have their maximum kinetic energy. I want to clarify because I just misspoke. And then by the time they're stopped by the stopping voltage, they're going to have no energy, because they were initially accelerating, and they got up to some maximum height. Essentially, they went up into a potential, not a gravitational potential, but rather an electromagnetic potential or electric potential. And they got to that maximum height, and they were momentarily at rest. Right? That's why the K final is 0. Okay. So then this is the change in kinetic energy of the electrons. Okay? And the reason it's max is because the freed electrons, the liberated electrons, have a whole bunch of values, okay, because they're not all being directly hit by photons. It's a whole spectrum of a probabilistic curve associated with it, but we're only interested in the maximum ones, okay, because we're only interested in the stopping voltage that stops the current entirely. Thus, it's also stopping the most fastest of the electrons, those with the greatest velocity, okay, those with the greatest kinetic energy. Okay, so then the formula is really going to be using on this next line down. Okay, so that says then that the maximum kinetic energy possessed by an electron is going to be equal to, you think about it because it's a negative and negative, so in magnitude and value for that matter, the maximum kinetic energy of the electrons is 1/2 mv max squared, which is exactly equal to the fundamental charge times the stopping potential. And now we relate it to the material properties of the metal. Okay, so this right here is specific to whatever metal is having light shown onto it. Specifically this right here, that phi. Okay, so HF is the energy of the incident photon. No surprise there, because it's literally just a repeat of above, but I'll relabel it. So HF. Okay, do it like this. Okay, so this is the energy of incident photon, okay, each one, okay, because we're shining monochromatic light, so every photon has the same energy. And then what's that phi, right? It's not an angle. I know it's weird, but this is all we always use phi for the work function. It actually has units of joules, okay, so it's phi representing something other than an angle, and it's the work function of the metal, Okay? So the work function of the metal. Okay? Units of joules, because it has to be, right? Because these are both, this is joules minus joules, it's delta energy, and that delta energy, whatever is the difference, the leftover energy, is how much energy the electrons can have. Okay? All right. Makes sense, right? Hopefully that's the idea, right? Where, just to summarize, we're shining light in, the energy of the light goes into the metal. That energy has to permeate the metal, which is why we subtract out the work function, because that represents the metal's hold on the electrons. Okay? But if the energy of the photons is big enough, then it can more than give up enough to the metal to overcome the work function, have some leftover energy. That leftover energy becomes the kinetic energy of the electrons. Now that energy is in motion, it's out of the metal, it's moving through space, okay? It would just go flying off, but then in order to measure it, we have it go flying off into an electric field that we can calibrate in order to stop them, thus measuring the maximum kinetic energy that those electrons had, thus perhaps measuring the work function or whatever it is we're seeking to find. Okay? Now, hopefully the lab that you worked with in the simulations kind of gave you some practice with this. But now let's look at some problems, look at some examples. All right, so I'm going to show you two examples. We're going to skip over example 4, even though it's a very good problem about photons in general. It's not a good fit for the photoelectric effect, so we'll skip over it for now. But let's take a look at 5 and 6, and then I'm going to be leaving 7 for you to work out on your own. Let's just double check that. Yep, yeah, so I'm going to leave example 7 for further practice, but I'm going to show you solutions to 5 and 6. Okay, so let's do it. So let's take a look at example 5. When 180 nanometer light falls on a metal, the current through a photoelectric circuit can be brought to 0 with a stopping voltage of 1.74 volts. What is the work function of this metal? Okay, so this is kind of typical of the type of information you'd be given, right? So now let's put it to practice, because you got it. There's a lot of variables to consider here. How do you actually solve one of these photoelectric problems? Okay, oh, so quick check here. 180 nanometer light, visible or invisible? Yeah, it's ultraviolet. It's invisible light, right? Because it's a shorter wavelength than visible light. Okay, so it's bluer than blue. It's 300 nanometers, about the highest energy blue light we can see. It's shorter than that. It's higher energy. It's the type that gives you sunburns. Okay, all right. So we're going to use the stopping voltage times the fundamental charge of the electron is equal to the incident energy of the photon minus the work function. Okay? We're going to go ahead and find the frequency of the light given the wavelength that we have. Okay, so we need F. So F is just going to be equal to C over lambda. Okay? Now I could just substitute that in the problem. I'm just going to go ahead and find F numerically. So we know the speed of light is 3 times 10 to the 8 meters per second. And we're told that our wavelength was 180 nanometers, so that's 180 times 10 to the negative 9 meters. All right. So let's see, what does that give us? I actually ended up substituting it in. But here, let's go ahead and get that. Yeah, actually, here, let's backtrack, because I didn't solve that numerically. So I'll just leave that as an extra step, and we'll substitute it in. Okay. So I'm just going to replace F with C over lambda, so that we'll just use the values that we're given. Okay, so we want to isolate the work function here, again, in joules. So that's all really what we need to do here. So I'm just going to solve for phi. Okay, if I do that, and I substitute in F as C over lambda, then I'm going to get E V naught. Not quite, actually, because I'd add it to both sides, and then subtract. Let's see, so... So I want to have it should be HF, right, yes, so it'll be HF minus, right? So H times C over lambda minus E times the stopping voltage, okay? So Planck's constant, speed of light, wavelength of the incident light, charge of an electron, stopping voltage, okay? We know all those things, so let's plug them all in. Okay, so we got Planck's constant, 6.626 times 10 to the negative 34 joule seconds times the speed of light, 3 times 10 to the 8 meters per second. And then we'll divide that by the wavelength, And we could have found the frequency, I just decided not to, if you're wondering why I kind of had a false start there. 180 times 10 to the negative 9 meters. There we go, okay? And then we'll minus the fundamental charge, 1.602, and you can use 1.6. It's fine to forget the 2. Times 10 to the negative 19 coulombs. All right, and then times the voltage that we told we were measured. This would be like in a laboratory experiment, 1.74 volts. All right, so then that gives us a stopping potential of 8.26 times 10 to the negative 19, look more like 19 joules. Okay, that's our answer, and it's fine to leave it in joules unless I explicitly ask for it in another common unit that we're going to be using a lot and have started using. That's the unit of electron volts. It's just another way of measuring energy, in particular where you have small energies. You know, so really no one would talk about, if you looked up tables of stopping potentials for common metals, your work functions for common metals, you're never going to see them measured in joules. They're always measured in electron volts. It's nice because you can kind of have these, these numbers that are between 1 and 10. And so it turns out that's equal to 5.15 electron volts. Now the conversion from joules to electron volts, we've already seen in this very problem, it's 1.602, right? Because remember that 1 electron volt is 1.602 times 10 to the negative 19 joules, okay? And that's because a volt is defined as the potential energy that an electron gains by moving through an electric field, right? So that the very definition of the volt is based on E, thus the conversion between electron volts and joules is, well, the same as the fundamental charge numerically, okay? All right, so there is our first example. Let's take a look at the other one. We're just asked to solve for different things this time. All right, so the threshold wavelength for emission of electrons from a particular surface is 320 nanometers, okay? And remember, that was the big conclusion that Einstein came to from the photoelectric experiment, is that there's such a thing as a threshold wavelength. Because if light was really just a wave, there would exist no such thing as threshold wavelength. Light would just liberate electrons, especially really high intensity light. Okay, so what will be the maximum A, kinetic energy, B, velocity of an ejected electron when the wavelength is changed to 280 nanometers? Okay, all right, so no mention of stopping potential here. So, right, this is kind of taking a different tact. Instead of kind of running a circuit and finding how much voltage we need to stop the current, we're just kind of freeing the electrons and imagine we have some way of measuring their electric energy, which could in reality be difficult to measure. But here we're just at least going to solve for that kinetic energy gained by the electrons. Okay. So, take a note here. Since lambda equals 320 nanometers is threshold wavelength, the kinetic energy would be 0. And not just any kinetic energy, the maximum kinetic energy. Then K max equals 0. Okay? Okay, let me elaborate on that briefly, right? Because I don't want to mix up very similar ideas here. Having a Kmax of 0 when you're applying a stopping potential is not the same as having a Kmax of 0 when you're at threshold. Okay, why is that? So having a K final of 0 when you're applying a stopping potential means that that electron came shooting out of the metal, but then after it was out of the metal, you stopped it with a circuit and a opposing voltage. Okay? On the other hand, when you're at threshold, right, when you're applying a threshold wavelength, that means that you've freed the electrons, but all of the energy of the photon went to the freeing, the liberation process, and there wasn't any left over for kinetic energy. It's where HF exactly equals phi. Okay? HF equals phi. There's no leftover energy. You really wouldn't notice it's happening because sure, there's freed electrons, but they're freed in the sense that they made it through the surface, but that's it, right? They'd be kind of undetectable unless you had some way of measuring like surface effects, So I suppose there would be a different distribution of charge on the surface due to this shining light on it, but it wouldn't be an external effect relative to the metal. Okay. Okay. So, the formula basically, I put in parentheses, but I'll just say, thus from K max equals HF. Let's see, am I saying that right? I just want to make sure I'm consistent with my own formula. Yeah, K max, good. Yep, so that's K here, of course, stands for kinetic energy. I know sometimes you write KE, but to be shorter, just writing K. So H, not subscript F, HF minus phi, all right? We get HF equals phi, okay? So the photon energy exactly equals the work function energy, okay? So that case is going to be pretty easy to solve for the work function, which we're asked for which we'll need actually for part A. So this is all kind of a preamble to part A. So then the work function would just be HF. Again, we are not given F, we're given lambda. Again, it's the more common thing to know. And the reason it's more common to know lambda is because think about how we measure light, right? We measure it with diffraction gratings, we measure with prisms, and in those cases, the physical thing you're measuring is the wavelength. Yeah, good luck getting an experiment you're directly measuring the frequency when these frequencies are vibrating billions of times per second. That's really why the wavelength shows up so often. Okay, so it should just be HC over lambda. Okay. So I'll plug everything in. 6.626 times 10 to the negative 34 joule seconds times the speed of light of 3 times 10 to the 8 meters per second, all over our threshold frequency of 320 times 10 to the negative 9 meters, gives us a work function of 6.21 times 10 to the negative 19 joules, which I'll go ahead and leave in joules because we're just going to use it, and I might as well keep it in base units. Okay, so negative 19. Okay, all right, so now actually on to part A. Okay, because that's the whole thing, right? In part A, if we tried to solve for K max, we would have had two unknowns, right? Because we wouldn't know K max, we wouldn't know the work function. So the key idea is that we use the threshold frequency that we were given in order to find the work function, so then we could actually answer part A to find the kinetic energy when we change that frequency to a lower frequency, okay? Or excuse me, to a lower wavelength, thus a higher frequency, thus more energy per photon. Okay? So what does it look like now? Okay, so now K max, when we change everything to 280 nanometers instead of 320, is going to be HC over, and I'm going to call this lambda, let's call the threshold frequency, let's call it lambda naught, because that was just enough to free it. See, did it come up anywhere else? Yeah. And let's just call this one lambda 1, okay? Because now it's some newer, shorter wavelength, higher energy, okay? Minus the work function that we now know. Plug in all our numbers, 6.626, getting tired of that probably. Negative 34 joule second, speed of light. Okay, now we'll divide by a different value here. And since we're dividing by a smaller number, that's making this first term larger, which is why when we minus the work function, we're not going to get 0 anymore. We get a positive term. So 280 times 10 to the negative 9 meters minus 6.19 times 10 to the negative 19 joules. Okay, again, which we solve for with the threshold. And that comes out to be 8.87 times 10 to the negative 20 joules. Okay, that's how much kinetic energy the most energetic electron, the one that was smashed into in a direct hit by a photon, that's how much kinetic energy those electrons would have. Okay, not a lot of energy, but remember, this is an electron. How fast is it going? Well, we can find its maximum velocity by simply relating k to, its form, 1/2 mv squared. Okay, so then we'd have k max equals 1/2 mass of the electron, V max squared. So then go ahead and solve for V max. And we obviously will have to square root both sides. And so we're going to have 2 times K max divided by the mass of the electron. Okay. So what does that look like? So that will be 2 times 8.87 times 10 to the negative 20 joules. Okay, that's how much those most energetic electrons are getting in terms of their kinetic energy. And then divided by the mass, 9.11 times 10 to the negative 31 kilograms. Okay, that's the mass of the electron, a constant that you would have access to, such as in your formula sheet. And that gives us, let me just give just enough space to write this value down here. Okay, so that gives us a value of 4.41 times 10 to the 5 meters per second. Not so sluggish, right? Tiny amount of energy, but very, very tiny particle. So in fact, these electrons, in this case, with the higher energy photons, are not just being liberated from the metal, but flying away from the metal at a speed of 4.41 times 10 to the 5 meters per second, or 441,000 meters per second. Okay? Here's a question for you. Should we have to worry about relativistic effects on this, right? Should we, is this fast enough to be concerned about a large percent error of relativistic effects? No. Okay? Could I give you a problem like that? Yeah, I suppose so, right? It'd be a difficult problem because you might not see it coming. But yeah, that would be fair game, in which case you would just have to use the formula for relativistic kinetic energy. And the way you do it is you'd first of all use the classical formula for kinetic energy. If you get a value that's close to the speed of light, so greater than 10% of the speed of light, then you correct it, use the relativistic kinetic energy formula, and then solve for V. But in this case, we're moving, a 1,000th the speed of light, so we're fine. Okay? All right. Well, thank you for watching this video about solving examples that involve the photoelectric effect. And please tune in to the third video where we're going to talk about Compton scattering, which is photons crashing into electrons, just electrons floating in space, rather than with the photoelectric effect, which was photons crashing into metals. Okay? So again, thank you for watching.